you like? It's your own style. Yeah.
Because we didn't say it before.
The other one. Yeah.
Real fast.
Good, yeah.
Sorry.
Good job.
I tried. Hello everyone, I'm Karima Maldonado and I'm pleased to introduce the speaker for today, Matt Hitchman. He's a professor from this department and he joined this department in 1986. So previous to that, he's completed a bachelor and PhD in atmospheric science from the University of Washington. And his most recent award was the AOS Graduate Student Award for Excellence in Teaching in 2016. So without further ado, please join me to welcome Matt Hitchman.
Okay, thank you. Yes, I think this is a contribution in the style that, in which we first envisioned this department seminar, that it was going to be a venue for people reporting on their master's work first, and then there's other categories like work in progress. So this is work in progress. Just working on it over the last while to prepare this talk, we figured out more new things, so it's pretty fun, but it's definitely a work in progress. Yeah, I guess I really should give my full respect to people who are true experts in tropical cyclones, and there are many of them. And so this is just kind of a humble contribution. About, I guess, a year and a half ago, I thought, how are we going to characterize these kind of blotchy patterns? And I was interested in azimuthal asymmetries in tropical cyclones, and so I cooked up this idea of maybe if we broke it into quadrants and looked at the variance here, that there might be some interesting information, means and variances, to try to categorize these structures. These are kind of curvy-shaped gravity wave slash PV dipoles, and nobody really understands them yet, so we're just trying to explore this. Let's see, any other prefatory? Oh yeah, so authorship. First of all, this subscript here, number 1, February 1. So this is Groundhog's Eve we can celebrate today. No, I meant this superscript here. Shelley's name is first on this paper that we submitted to Monthly Weather Review last fall. And the reason is, well, Francis Brotherton said, and I still like this, that every author knows that they did 80% of the work, right? I still like that. And that's how I feel. I did the index, and I wrote some, and I like to think about things. But Shelley, just completely independently, a year and a half ago, started working on this case. She felt that the South Pacific tropical cyclones were understudied, that everybody looks at Atlantic hurricanes or maybe Northwestern Pacific hurricanes, but the ones that meander all over the place in the South Pacific are strange. Let's take a look at one. So that was the history behind why we did this. I'd also like to point out that this technique, which is just really simple statistics, it's RMS and means, and then just thinking about what they could mean. But Dan Forte is going to be using this. He's in the process of assessing 7 Caribbean tropical cyclones. It almost sounds like 7 seas. We're kind of high. And so look forward to his presentation perhaps next fall. And I believe he also has a poster coming up as well next week, I think. What else? Yeah. I guess I came at this from the point of view, I have a long-term interest in inertial instability. So when I did my PhD working on the tropical middle atmosphere, I realized inertial instability could explain many of the features there, these pancake structures. And so that's been a common thread throughout my career, is to try to understand inertial instability better. I feel like it actually is capable of explaining quite a bit more than people realize. It's really fundamental. So I've been working on that approach for quite a while. So here's the organization of the talk. First of all, I'll describe other people's theories and our own theories of how PV dipoles form in the upper troposphere and lower stratosphere, which we call the UTLS. That's maybe a scale height thick, 7 kilometers or so, upper troposphere, lower stratosphere. Then I'll introduce this new cloud top PV variability index for tropical cyclones. Of course, the reviewers were very upset that I used the word new, but this is actual English, and it is an index, and it is new, but excuse me, they're going to have to deal with it. There's two approaches. One is divided up into quadrants, and another is to divide it up into analyses. And the reason for this is there's a thread of literature which talks about the Diurnal cyclone, tropical cyclones. And when Jason Dunyan came here, and he's given, I think, maybe 2 or 3 talks in this department, it really caught my attention. I thought it was a fascinating study. So we'll weave in the Diurnal cycle into this talk as well. But mostly I'll be talking about the quadrant method, and Dan will be reporting on using the annulus method for those Caribbean tropical cyclones. We make use of this fantastic new data set, which has been available since about 2018, and it's 0.08 degrees resolution. This is ECMWF data, and they produce potential vorticity. Another complaint by the reviewers was, you don't have potential vorticity on theta surfaces. I said, no, this is potential vorticity produced by ECMWF. And if you want to question that and quibble with it, I guess you can go grapple with ECMWF. I mean, all right. They also have humidity, which is of interest. And then we can also make use of, in this quadrant, Himawari 8, cloud top temperature and pressure. This is a more traditional approach, right, to get a feel for what's happening in the cloud tops of tropical cyclones. A brief mention, a few slides on why the South Pacific tropical cyclone regime is of interest. And then we'll focus on tropical cyclone Yasa, and that occurred near Fiji on December 12th to 20th of the year 2020. The highlight, the first result that we had, I still think is salient, that there's a diurnal cycle in the RMS variability of potential vorticity at this scale at 100 hectopascals. And I chose that level because it's near cloud tops. So I was interested in what these features are doing. So we'll then look at the evolution of mean PV, and as well as the variability of PV in time altitude. And I'd like to call these things full storm evolution. It's got a resonance, you know, like whatever, something Doppler radar. It'll become popular, don't worry. We'll take a first look at specific humidity, which is interesting and confusing. And then we'll ask, are there common dynamical patterns? When I thought I'd give this talk, Shelley said, let's check a few more tropical cyclones. So we'll get to meet Harold and Winston too and examine whether or not they have similar properties to what we found with Yasa, which is a good check. All right, a little bit about potential vorticity and how it relates to inertial instability, because it's just a core aspect of what's happening here. You probably know this, that it's a famous central core idea behind how the Navier-Stokes equations were proven to be essentially correct, an agreement between laboratory and theory for this situation of inertial instability. All that happens in this condition is parcels try to accelerate and rearrange themselves to create a more stable angular momentum profile radially in a vortex. And the condition for instability on a sphere is that F plus zeta z, the vertical component of relative vorticity, becomes negative in the northern hemisphere or positive in the southern hemisphere. And the key aspect for PV dipoles is the smallness of this scale, dBdx, or y. This is like 50 to 100 kilometers, which makes this big. And it's routine that zeta z is bigger than and less, is negative and bigger than F in these PV dipoles in the northern hemisphere. But we should note that in the southern hemisphere, where F is negative, what we look for is anomalous potential vorticity, so that the absolute vorticity would have to include relative vorticity that's positive. So we look for anticyclonic or anomalous PV in the southern hemisphere, so PV positive. You might say, how can you say PV positive? Well, in the special case of the UTLS, when updrafts ran into the base of the stratosphere and stopped doing that, d theta d z is positive. Okay, so the convective impulse to rise, because d theta d z is negative, has gone away once you punch into the base of the stratosphere. So somehow, magically, negative PV in an updraft can be converted to a pair of a dipole, with one of them anticyclonic and inertially unstable. And that's where the mass spews out of it. It's the negative member, the inertially unstable member, that's where mass comes out of individual thunderstorm turrets. And when you agglomerate them all, add them all together, aggregate them, that is the inertially weak or unstable outflow at the top of tropical cyclones. A lot of people enjoy thinking about potential vorticity budgets. This is a fairly clean conceptual breakdown, although you'll see very many different types of formulations. This says you can change potential vorticity following the motion if you have a tangential, sort of frictional or maybe gravity wave stresses that act azimuthally. Then you have the classic vortex stretching. If you have Q maximizing in the middle, you'll have vortex stretching in the lower troposphere and then vortex shrinking in the upper troposphere. This can produce a PV dipole if there's also shear, but that would require a separate process. Here we have an explicit combination where we have the gradient of heating horizontally times the vertical wind shear. So these are classical tilting twisting terms that are based on latent heating in the problem that we're looking at. If you really want to do a budget like that in isentropic coordinates, it's challenging. So you can get data sets that are in isentropic coordinates, but there are two problems. One is those must have been all smooth so that you have a monotonic coordinate in the vertical, so there's no convective instability in those data sets. Also, no inertial instability. It's probably smoothed out. So I wouldn't look at that myself. Another problem is boundary conditions in sigma coordinates, or theta coordinates, I meant to say, theta coordinates. So, a lot of people merely go along analyzing potential vorticity, just the vertical component, on pressure surfaces because it is widely available from ECMWF and other data sources. Okay, so to get at the heart of what's going on with horizontal PV dipole production, this has an interesting history. Davies-Jones, you really have to go back to Davies-Jones in 1984. He's still writing papers. I just saw another one that came out. Very careful thinker, and he said, look, it's the same thing whether you have an isolated hill or an updraft, that if you have any environmental shear, there'll be horizontally oriented vorticity that's tilted into a horseshoe shape. It's inspired textbook renditions of how tornadoes are formed, even this concept. Chagnon and Gray really hit the nail on the head for how horizontal PV dipoles can be formed in the troposphere from an updraft. I'll show you that figure in a second. Here's a couple of other examples of fine papers in this regard, and they all say horizontal PV dipoles can be formed by updrafts and horizontal wind shear, and the tilting of the horizontally oriented vorticity associated with that shear into the vertical direction creates a pair of counter-rotating vortices on either side of the updraft. So this is all established theory. Chagnon and Gray chose Q. This is their PV. It'll change in time. If you have a classic situation, you have ambient vorticity, the planetary vorticity that can be operated on by the differences in the rising motion. So that B stands for buoyancy. You could think of W as well. And so this is just the vortex stretching compression by latent heating. This one is a tilting twisting term. You have a classic dEdz times dWdx, essentially. And to interpret this, these arrows show the mid-level shear vectors. So that means you have vorticity directed into the border of a positive y-axis. It's a sheet. But if you have differential vertical advection, one spot where it's going up and everywhere else it's not, that's right, here's the updraft. Then it takes a tube of vorticity and it bends it up. Here's the positive side. Up and over and down, here's the negative side. And if you slice through it, lo and behold, you have a PV dipole. So when I saw that, I thought, this is pretty cool. This is right about the time when I started thinking about PV dipoles. Another really important thread, and people in the applied math department here on campus already have several papers in this area. This may be the most famous one. This is Chris Snyder et al. 2007. Everybody who says that you have to have high resolution to publish an idea, better look at this paper. This one is I think it's at 12 kilometers resolution. Right? Never mind, what's a different topic? Okay, so they study PV dipoles and geostrophic adjustment. Here's a swirly, and here's a jet. If you have a jet, you have a pair of counter-rotating vortices. If you have a pair of counter-rotating vortices, you have a jet, but it's axiomatic. It's just topological. It's so fundamental that that's just the way it is. One goes with the other. So they have these, what they call balanced vortices, but I would say no, the key aspect of this is these are balancing vortices. They're in the process of coming into equilibrium, otherwise they wouldn't be radiating gravity waves. This pattern is vertical motion, so if you slice through here, you can see, oh, there's upward motion there, and there's downward motion there. And if you look at zoom in on this portion of it, you can see there's this upstream tilted structure, gravity wave energy going that way, phase coming down, opposing the flow. So those are gravity waves. They're intimately involved in the adjustment process. This one is, I guess this one's the anticyclonic one. And if it's strong enough or a small enough scale, it will be inertially unstable. So this is another important part of this, is the whole realm of how does flow adjust, and how is inertial instability related to it? How is it related to gravity wave formation? Is there something going on with gravity wave radiation and PV dipole formation by an updraft? Okay, so these people are all into this sort of idea, for sure. So don't forget about gravity waves, because it'll help us really understand what's happening. All right, in 2017, we published a paper where we tried to find a commonality of structure and dynamical behavior for dipoles for tropical cyclones and also mid-latitude cyclones. This is a Super Tuesday mid-latitude cyclone that you might remember. Maybe 2,000 cars were stranded on 94 between Madison and Janesville. South of here, there were, I think, 78 deaths from tornadoes in the Mississippi Valley region. So it was very intense. But look at this PV dipole. These are in PV units, and I've converted everything to PV units, which is 1 times 10 to the minus 6, and then some units. K meters squared per unit. I don't always remember that. But these are PV units, and this is negative and this is positive. So this is to the left of the shear, and this is to the right of the shear. In this case, here we have negative PD on to the right and positive PD to the left, but the shear is that way. Why is that? Because the location of this picture is about 200 kilometers to the east of the surface low, and that means that the mid-tropospheric flow is like that, but this is up above that. This is in the anticyclonic outflow region. So if you take, say, 50 meter per second northward flow and rapidly vect it up to this level, there will be a jet compared to its environment, which means you have to have this. And because it's about the scale of the updraft, it is a small enough d by dx in the denominator to make the relative vorticity strong enough so that it's inertially unstable. So first of all, the mid-latitude case, if this is northward, you often have northward shear to the east of the trough, and if you have, and so that means you have say a westward directed vortex sheet. But if you have an isolated point updraft, then it'll tilt the tube up and down and create this PV dipole with positive to the right, negative to the left. That's the mid-latitudes. And in tropical cyclones, the shear is the opposite. You have very strong cyclonic flow in mid-levels, but it weakens to the top and it reverses sign, right? In the UTLS, it becomes anticyclonic outflow, very weak divergent flow, maybe 5 meters per second, something like that. And so the vortex tubes are directed outward, radially outward from the center of the tropical cyclone. And then if you impose an updraft, that means that the portion pointing up is to the left of this updraft, and the negative one's to the right, which is also radially outward. And this simple diagram, if you add all the ones up like it in a tropical cyclone, what you get is a ring of high PV in the inner core, which is correct, and low PV on the outside, which is flowing outward, which is also correct. That's what Mesoscale and Tripoli said. You know, that's a very common thing around tropical cyclones. Big plumes of weakly inertially stable or even unstable air rushing out, sometimes going forward and interacting with mid-latitude jets. So there's a lot of interesting work done on that process. And I guess we fit into that a little bit by looking at more at the sort of mesoscale of how that plume begins. These factors may be of use. If you think of a difference of only 20 meters per second across 100 kilometers, well, that's twice the size of F, so it's adequate. And it's because of the small scale to have it be inertially unstable for the negative member. And this factor here, 1 over rho theta dc for PV, it's 20 times bigger at 16 kilometers relative to 6. So that's partly why UTLS PVs have PV dipoles have a large amplitude compared to the mid-troposphere. But there's also something special about the static stability being weak, and then all of a sudden strong. And when you hit the bottom of the stratosphere, it's like hitting a drum. You pick some vibrations, gravity waves radiate. And strange things are happening. And this is sort of a wonder to peer in and try to sort out what it is. Another line of reasoning in our field against this whole idea is that if you're talking about geostrophic flows and coming into balance, that gravity modes have nothing to do with it. I don't know. There's a lot of people that think that. I think it's the opposite, that the adjustment process requires gravity waves, which is what Rossby said in the first place. I mean, I don't know how to get around that. But also, maybe in the case of convection and adjustment related to it, that there are mesoscale inertial instability features that might be important too for adjustment, and that they're related to gravity wave things. Here's just one sample. This is from simulation of tropical cyclone body. It's not a perfect mapping, but yeah, this is high PV, that's low outward. This is high PV, low on the outside. And then if you put winds on, you can see, oh, there's a lot more outflow from the inertial unstable member. That's where the stuff comes from. It goes up in the updraft, which doesn't coincide with either the positive or negative reliably. That relationship is complicated. We've looked at a lot of PV structures in 3D in the middle of clouds and tops of clouds, and it's complicated. Anyway, so let's proceed. We published a paper in 2019 where we compared these PV dipole structures in 3D tropical cyclones, and we thought, you know, I like to kind of sit there and think, can I distill this into something I can remember forever? Sort of simplify things. And yes, I can do the vortex tilting tube into a horseshoe shape in my head, yes. But you can understand it even more fundamentally, and it's a little bit simpler because you take away one of the spatial derivatives. So, yeah, we'll get to that. But the basic principle is the convective momentum transport principle is if air is transported in the updraft into an environment which has a different speed and direction, you're going to create a mesoscale jet with an associated PV dipole in the horizontal plane. This also works for downdrafts. So we studied a derecho, and in the downdraft, it coincides closely with negative PV, and ahead of it to the east, there's a positive PV anomaly, and behind it, there's a negative one. And the southward jet between the two leads to this outflow layer, like a snowblower blowing snow to the right. I kind of think that's a fun analogy. So maybe this is it's such a simple bonehead principle. Yeah, if you invect momentum upward, it'll change what's happening somewhere else. I kind of like that, simplicity. What other things did we find? I already said this, divergent outflow is predominantly from the inertial unstable member. These things generally occur not right in the inner eyewall, but somewhat farther out in convective clusters. And in the numerical simulations, within these convective clusters, there would be a surge, inclined acceleration in both the horizontal and vertical acceleration. You know, updrafts and hurricanes are like an angle of 8, they're not very vertical, they're huge zenith angles. Also, convective asymmetries associated with PV dipole jetlets can significantly modify tropical cyclone evolution through local thermodynamic acceleration. Have you heard of this idea? So most theories for tropical cyclones in the 80s and 90s were axisymmetric, and there's a huge core of that, and it's very valid, it's important. But if you think about it, if you look at a tropical cyclone in satellite data, there's a whole bunch of little blobs, and those are actual clouds, and that is what a tropical cyclone is. It's a bunch of clouds added together. And this is Michael Montgomery's point of view, and a growing body of literature in this vein says that TCs grow from the aggregate of energy conversion in convective clusters. It just projects onto a zonal symmetry. That's a different point of view, isn't it? All right. This is the crux of how you produce PV dipoles in tropical cyclones. You have a cyclonic poleward flow here on the east of the low, and you just bring that momentum up here, it's going to create this jetlet, which is the opposite sense of that. So relatively speaking, you have this polar jetlet in the UTLS, which requires this, and to the right, it's inertial unstable, often, most of the time. And it predicts the orientation in TCs, like I just showed you for tropical cyclone body. In the northern hemisphere, if you invect this cyclonic flow upward, then get this jetlet at the UTLS and this sense of rotation. Same thing here, you deck that upward, you have an anticyclonic outward member. In the southern hemisphere, the same is true. You deck this cyclonic flow upward, and on the outside here you have the anticyclonic member, which is anomalous PV for the southern hemisphere, and it's inertially unstable if you have positive PV. And here's the complementarity of it. I'm just saying, if you want to know why there's polar acceleration at the UTLS, then you can advect it up from the middle of the storm. I like that idea. It's so straightforward. You can take the first derivative of it and show that it's the tilting twisting term. So either perspective seems fine to me. All right. So why did we do this? Why did we study tropical cyclone Yasa? We're interested in general in PV dipole formation, gravity wave radiation, and the adjustment process. This is probably my main motivation. Was we were struggling with how best to characterize PV dipole strength, size, shape, and number. They vary so widely from day to day, from hour to hour, from quadrant to quadrant in tropical cyclones, from cyclone to cyclone, from representation in different data sets. They all have different shapes and sizes and numbers, so what to do? And so I thought, all right, it's time to weigh in with a statistical approach. All right, so we also wanted to study the role of azimuthal asymmetries, and that's why I picked quadrants. We can maybe later have outward directed spiral fan shapes that more approximate, how air comes out of tropical cyclones through gouging. We can look at that. We're also interested in life cycle TCs, the Diurnal cycle TCs, because Jason Denny came and gave a talk here, a couple of them. It just was inspiring. But so we're making, as it turns out, we are making a contribution to half of this problem, the first half, the nighttime half of it. But I also have a speculation about the daytime half, and I'd like to see what you think about it. All right, so we're also interested in the vertical dependence of the signal in a tropical cyclone. We kind of naively expect a mid-level maximum where there's a lot of latent heating, and then a bigger maximum in the ETLS. That's just sort of intuitively, qualitatively what I expected. And then the storm tracks in the South Pacific are so complicated, they're just outrageous. I mean, the forecasting problem in that sector is probably harder than the Atlantic. I mean, it's pretty reliable. Most Atlantic ones do this, right? But in the South Pacific, no. And I think it's due to the existence of the South Pacific convergence zone. Makes it all different. So our assumption is, based on the convective momentum transfer principle, that the formation of these PV dipoles in ETLS should be a useful indicator of the activity of deep convection in the depths, throughout the depths of the tropical cyclone. What you see at the top implies something about what's happening inside. It's maybe even kind of a probe of what's happening inside, a proxy perhaps of this activity. And then our hypothesis was that the RMS variation in PV will exhibit a moderate mid-tropospheric maximum and a larger maximum in the UTLS. Luckily, that turned out to be true, so, all right. So these statistics are pretty simple. Just defined for like PV, you just form a standard deviation and mean, but we also are looking at, in addition to PV, we're looking at moisture, Q, take a look at that, and also we can look at cloud top temperature and cloud top pressure for minimal RA8 and treat it similarly. But then we realized, oh, we don't have to restrict ourselves to 100 hectopascals. And indeed, when you start looking at Winston and Harold, you realize, oh, some hurricanes are much wilder and deeper and more vigorous. One hurricane is not adequate to predict another hurricane's behavior. All right, so here's our spatial domain. This is, Dan's going to use this, maybe we'll add a fourth one, to look at this diurnal cycle. I might as well say it now. So the theory is, oh no, I have a slide on that, so that'll be better. For this talk, we're mostly using the quadrant method because I'm personally interested in, sometimes there's a lot of convection here, sometimes here, sometimes here, sometimes here and here. And I'm really interested in these zonal asymmetries because, I don't know, they're obviously not symmetric. So here's the data sets that we analyzed. The 9-kilometer horizontal scale, but every 6 hours in time. Oh, yes?
Are you using these quadrants relative to wind shear or just relative to track?
Relative to the location of the eye.
Okay.
Just the eye. And here's another data set which has a nice quality of every hour. And so we thought maybe we could resolve a diurnal cycle better this way. But it's 28 kilometers resolution, which really degrades the representation of these PV dipoles, which are like 50 or 100 kilometers. It's not very good. So for each 3x3 quadrant, we have this many values for a given time step for ECMWF, if you do the math, and about 144 of these values, and 23,000 of these values. So that's a pretty stable estimate of a standard deviation. If you add or subtract some of these randomly, you'll have about the same result. Well, here's just one example. This occurred for TC Yasa when it was just reaching category 5, and this is midnight Fiji time in December 16th. We'll do everything in Fiji time because that's more amenable to talking about the diurnal cycle. It's actually 12 hours earlier in England at this time. So here's PV at 100, and one of the curiosities is that it has spiral structures. It's not really nice blobby dipoles, right? We were thinking, oh, maybe they're smeared out by some process, but now I'm realizing, no, these are hybrid PV dipoles gravity wave radiation signatures. Both are mixed together. And it's like looking into something wild and new, like I don't know, help me. If you want to study this, I think it's going to turn out to be a pretty deep problem. Another interesting facet here, you can see the red and yellow portions. These are positive PV. That means in the southern hemisphere, it's 15 south. That is anomalous PV for the hemisphere. It's inertially unstable. And look, this band of inertially unstable air coincides with the spiral. All right, so this is confirming some of the ideas by Tripoli Mezakowski and also, was it 89, Robert Merrill, who used to work in SSEC. I think he wrote the first paper on this. All right. Just a little bit about the South Pacific and why it's interesting. Here are blue and red in cats 1 and 2, cats 3 to 5, and they're about 10 per year, somewhat variable, and about 5 intense ones per year. They tend to peak between December and March. I guess I'm going to show you one from December, February, and also April. And that's a pretty neat book, and this chapter is by a person named Chan. This shows that the whole system shifts westward. Here's the South Pacific convergence zone. At 850, you can see convergence in this diagonal pattern. And you've seen it on satellite maps. This is that big, huge southeastward extension of the maritime continent's cloudiness toward the south central Pacific. This whole thing shifts westward with La Nina years, as you might imagine. So it's very strong control by El Nino. And you can see that again. And maybe this is wise, and I'm doing this with the QBO too. Instead of getting things like westerly and easterly, no, there's a transition season, transition in one direction and also in the other direction. So he broke it down into El Nino, La Nina, positive neutral, negative neutral. I think these are the transitions between these two, maybe that matters. But you can see this nice westward shift for La Nina. And it's also an interesting region because there's fairly clear evidence that the number of tropical cyclones is diminishing with time. And I'm hoping that some of you are experts on why this is so, because this is in the forecast. Unless you're in North America and you're running the GFDL model, all of these simulations for all the tropical cyclone basins say that by the end of the century, there will be some 10–20% diminution of the number of tropical cyclones. Why? I don't know. Do you know? Why? No, I'm just not plugged into the community of these modeling groups. I mean, I can guess. I've heard things like the Walker circulation is going to slow down with increasing moisture, and so all the circulations will be weaker, including tropical cyclones. Is that true? I don't know. But that's what these models suggest. All right, so here is tropical cyclone Yasa, and one of the more wonderful things about this study is to really fully appreciate what it takes to try to guess at a storm track, and to guess at the sea level pressure minimum, and to guess at the maximum winds. Very hard thing. and all these different techniques. I was impressed. So here's the path. It meandered around here for many days, and then when it finally, and this is the interesting part as far as the Diurnal cyclone, a large PV variance here as a precursor the first 3 days, and then it took off, just ramped up within 30 hours from category 1 to 5, but when it hit Vanuatu Levu, it damped out, and then it headed south and died. So that's a fairly complicated trajectory, and I think this is an important part for this type of study. So we used the same storm track, but we compared it with estimates of the I's location by inspecting ECMWF 100 hectopascal PV. That is a model. It's got a whole bunch of things in that black box. It's not just observation, so it's not going to be the same as the real world. Convection in a model may have statistically similar properties, and the gross features might be similar to reality. But the detail of tropical convection, you know, is not an easy problem. And so it might not be the same. And so we made a track based on the location of the I as we could tell it in 100 hectopascal PV, and we also did it for cloud top temperature. Well, in tracing the difference between these three methods, sometimes the errors were 50 kilometers, most of the time less. And so I did a real simple calculation, and I think this means that sort of the jitter of where the edge is, you add and subtract data points, is around 10% uncertainty for it's introduced by that uncertainty of the storm track location. And for this particular one, for Yasa, we chose to use the cloud top PV variability. That's what we were looking at. So we based the storm location on ECMWF data. For Harold and Winston, we chose to use SIMS because it's a lot easier to take those columns of numbers and plug it into our algorithm. But we'll continue to track this issue as well. What is the uncertainty of the results based on lack of knowledge of the storm track exactly? All right, so why did the storm die out curving toward the southeast? Well, these temperatures are kind of nice, 29.5 degrees when it was brewing and getting going, but then passing the Vanuatu Levu, getting down here, it was getting to our 25 centigrade. So that's exponentially less water vapor for fuel at that temperature. Here's the SIMS mean sea level pressure going from 1,000 while it's building up. And then all of a sudden, December 15th, 6 p.m., midnight, this is an intensification phase on the evening of the 15th. And by 6 a.m. on December 17th, it was down to, this says 912 millibars. The wind speed started at around 40 knots and picked up to 60. Oh, that may get into the tropical cyclone category here, in blue and green, and then rapidly getting into red, and this is that black or dark red, and with speeds of 140 knots. Okay, so that's kind of the classic build-up and wind down. And this shows 8 days, they're 6 hours apart, so this is noon, 6 p.m., midnight, 6 a.m., and the same for each of these days, starting with the 12th going to the 18th. And if you're sitting in the way back, it might be an advantage that I would argue that this time, 6 p.m. is weaker than, for each of these days, than this time. Okay, midnight to 6 a.m., midnight to 6 a.m. And even here, midnight to 6 a.m. is a little stronger than these other times. It's hard to tell, a little bit hard to tell. Well, let's take a pair, just snapshot examples. This is 6 a.m. and 6 p.m. 6 a.m., that's pretty active. PV stuff, there's some PV variance. What is it? I don't know. I think if I were embedded at ECMWF with whatever, 200 people working there, and had access to all their manuals, secret manuals of things, maybe you could figure out a little bit more about how these are created in the ECMWF analysis. But there they are. Pretty weak at 6 p.m., pretty strong at 6 a.m. Is there correspondence here? Yeah, this looks more blotchy and vigorous, I think, to my eye. And maybe this inertially unstable area does correspond with that. Not always. It's not a straightforward relationship, but most often that's true. And you can see the grid that we use for calculation. So it moves around, and we try to put it at the center of what's going on. This is 2 days now, and you can see then Himawari temperature here on the left, on the right, and this is 100 hectopascal PV on the left. You can see it really ramping up here and then going away by 6 p.m. This actually agrees with all these other authors who have studied diurnal cycles and tropical cyclones. So that was nice. I thought, oh, hey, maybe this will be helpful. And here's the history of, a brief history of the diurnal cycle papers. Browner et al. In '77, he studied, or she, I don't know, the 8 Atlantic tropical cyclones. And this started it off. They said there's this expansion of a cirrus shield during daylight hours. Well, so I tried to look for that in all this data, and it's hard to see. PV at 100 isn't the same as other things that you could look at. Dunyan, okay, he used brightness temperature differencing, shows an outward progression during the daytime. And he used satellite infrared, and he looked at strong Atlantic tropical cyclones during that 8 or 9 year period. Then Melhauser and Zhang, they did a numerical study of tropical cyclone Karl, and they said, nighttime rate of destabilization is the whole key, and it ties in with the Carnot theory. If you have a bigger difference in temperature from the top to the bottom, you have more efficiency. I kind of like this theory. It seems pretty good. Bowman and Fowler looked at 1,500 tropical cyclones and found that the peak rainfall was at 6 a.m. That agrees with other wide variety of other tropical studies for other kinds of phenomena that rainfall tends to peak then. These other authors all confirm this basic idea, which is represented here. That in this 2-part system for the diurnal cycle for a TC, the inner core grows rapidly at night when the cloud tops are radiating to space, instead of being exposed to solar heating, makes it more efficient. I kind of am comfortable with that. All these authors were groping for an explanation of the daytime phase, the second half, and they say, they have plenty of caveats. They say, we don't know, this is our speculation. Daytime expansion of the cirrus shield is due to solar heating, which promotes lofting and outflow. Maybe so. Maybe so, don't know. All right, this was our first result, and it was kind of exciting to get such a strong cycle, diurnal cycle, in the variability of PV at 100 hectopascals, right at the cloud top. So this is for each of the 4 quadrants. First of all, the timing, 6 a.m., 6 a.m., 6 a.m., 6 a.m., midnight, 6 a.m., midnight, midnight, midnight. All right. It is at least consistent with all of these other papers, but I still don't know what it means. Okay? Here's another factor. The first 3 cycles are huge, and all the rest of them are pretty robust, although it wanes in sort of phase relationship amongst the 4 quadrants, but there's still a pretty significant diurnal cycle. A big reduction from the spin-up phase to, as soon as it starts growing and really getting strong, that phenomenon goes away. And so I thought, just possibly, maybe it might work out that if you looked at 100 millibar PV in ECMWF data, and you looked at a tropical cyclone right now and you saw this sort of thing, you could guess that perhaps it might grow and it might strengthen. So could it be possibly useful for forecasting? Maybe, I don't know. Maybe. I have a lot of humility with respect to that. I can see everybody trying so nobly in understanding easterly waves and the subtlety of what are the conditions that will allow it to grow and to not grow into a TC. That's very careful work. All right, so what if we averaged over all quadrants and then looked at 100 hectopascal PV variance? That's this one, so this is averaging over all the quadrants, and it's pretty robust. We hope to gain a little bit more information by looking at the 1 hour ERA5 time resolution, and that's in the lighter curve. You can see more detail. I don't know. Is this different from that significantly? I don't know. Look at it. It just kind of falls apart when the phenomena get weaker. Guess you need to have both high spatial resolution and high time resolution to look at this problem. But if I had to choose, I'd go with the higher spatial resolution. So that's why we emphasize the 9-kilometer data. Here's one way to look at the time The vertical variation, yes, there is a mid-troposphere peak like we expected, but look at this whopper centered on 100. And it's biggest in the first 3 days, and then it gets smaller. Here's, yeah, I want to call this full storm evolution plot. So you take the storm in the 4 quadrants, average over all 4 of them, and track it following it, and you do the whole vertical, the whole full vertical dependence of this problem. So this is following the motion of the tropical cyclone. A really interesting thing emerges at 100, but also at 70. Above the tropos, you have this peak of the PV variability, and it continues, but at a smaller amplitude after amplification. There's also a mid-troposphere kind of lens of high variability that coincides with the maximum in the storm strength. But then I think we have a little bit of handle on what this is, but this is odd. There's a pronounced minimum in PV variability at 250 and 200 and 150. While this is happening, while this is strong, and then that goes away. Well, there's a little bit of it here. Huh, okay, and then here's another one. I don't know, I guess this is boundary layer convection? All these things, I just don't know yet. It's going to be fun to look at. All right, you can zoom in on the UTLS, that's just 350 to 50 hectopascals, and see a little more detail if you want. And then it's also important to look at the full storm evolution. No, that's not going to take off, is it? Come on, full storm evolution. Oh, well. This is mean PV in a time height section, and you can see the tropos here. Mean PV has an interesting signature too. This is the storm growth. This is negative PV, but that means cyclonic in the southern hemisphere, and then it kind of fades again. There's this, inertially, almost inertially unstable. This is about 0 here in the uppermost troposphere, at the same time that there were these huge diurnal peaks in PV variability. What's that? You see, this is, and so anyway, that's why it's good to check other tropical cyclones, right? But is this a robust thing or not? You can compare, you can try to look at PV is kind of weak, getting towards 0 here during the rapid growth phase. That's consistent with Carey Emanuel's theory, is if you have more rapid ease of outflow, then that can also improve the efficiency of the tropical cyclone. And so a lot of PV variability at the tops of the tropical cyclones, and weak inertial instability during this rapid growth phase. This is a dip into humidity at 100 hectopascals. Humidity rises and rises and rises and rises and rises. And here's PV. It tends to get more positively cyclonic as time goes on. But there's a lot of this time scale variations, and the correlation is minus 0.7. Why? What is that? We'll work on it. Maybe it's that when the whole storm is sort of expanding, it's wet, and so it encroaches. That means it's going to have pretty strong negative PV and moist. Sort of. Well, you can also look at variability in cloud top temperature. Not as coherent as PV at 100 for this diurnal cycle, but it's there. You can see sort of, kind of. So it's just a different entity. It's showing something different than PV. All right. Why does this variability increase in time? I think it's because if you imagine looking down at full strength, you see a uniform cloud top, so not very much variability, but as the storm is dying, there might be some tall turrets and some short ones and medium ones, and that increases the variability of the cloud top temperature. Probably, something like that. Okay, so this is conclusions part 1, and we think that this new cloud top PV activity index may be useful as a proxy for deep convective activity. It's based on the convective momentum transport principle, which suggests that you can generate mesoscale jetlets and eddies that you will have to. And the study of Yasa shows 100 hectopascal PV activity index is high, And there's weak inertial stability immediately prior to the rapid growth phase. Now, is this consistent across other tropical cyclones? We have to check. In contrast with the modest peak in PV activity in the mid-troposphere, which reflects maybe just the internal latent heating and cooling, the peak in PV variability in the tropos is very robust during the amplification phase and exhibits a strong diurnal cycle. Okay. Well, yeah, are these precursors in Yasa valid? Then is 100 hectopascals the best to look at? Let's try looking at other South Pacific basins, Herald and Winston. Herald is 3 to 9 April of 2020, and Winston is 14 to 22 February of 2016. So here's Tropical Cyclone Herald. It started off in the Solomons, headed toward Vanuatu, and then kept going past Fiji way over that way. Why not? That's what it did. Wait till you see Winston. Okay, so here's 100 hectopascal PV variability, and all right, midnight 6 a.m. 6 a.m. Midnight 6 a.m. 6 a.m. Midnight. Oh, okay. It's not as clean, but I suppose this basic paradigm is kind of in there. There's a signal there. But what's astonishing is these values in PV units that are like 6 to 8. But if you go up to 70, which is higher above the cloud tops, you get, on average, more variance. And then we realized, oh my gosh, we're looking at gravity waves too. And at 70, it's much more variable. However, the wave activity gets up, takes a while. Inertia gravity waves have short vertical scales. The propagation time scale for wave activity or energy might be comparable with this distance of 3.5, 4 kilometers from 100 to 70 hectopascals. Because, like, look at this. This is 6 a.m., that's 6 p.m. Noon, I don't know, but midnight. There's maybe a hint of a coherent diurnal cycle, but it's more random. And if you do the full storm evolution, okay, this is variance in PV. Look at up at 70, up at 50. Gosh. We still have some commonalities. High variability in the mid part where the storm is strongest, weak variability in the upper troposphere as it's developing, some kind of cycle and something happening in the lower stratosphere for dipoles and gravity waves. If you look at mean PV, Herald was a very vigorous storm, and throughout most of its life, it was either inertially unstable in the entire storm average at 100 hectopascals, or almost. And it was very vigorous, and the cloud tops were deep. It's curious that all those peaks in inertial instability are near noon. Maybe that fits into the puzzle. And then here's a PV evolution, mean PV. Again, somewhat similar. There's sort of a weak to almost inertial unstable in here. This is 0 here. And then the cyclonic maximum in the mid-troposphere. How about Tropical Cyclone Winston? Where did he start? Down here. Decided to go over there, and then over here, and then to there. I don't know, I kind of enjoy these storm tracks. You can see that it was strongly developed centered on about 19 February. So these two are hot off the press in the last few days. Tropical Cyclone Winston. Oh, Winston's a bad boy. He's got an independent spirit. Perhaps even smokes cigarettes. I thought I'd risk that joke. With no disrespect. But anyway, so yeah, peak at midnight, 6 a.m., noon. Nah, that doesn't fit the paradigm. Noon? What? Hey, all right. There's some sort of interesting variability associated with Winston anyway. Doesn't really quite fit the paradigm. At 70 hectopascals, there's a lot more. Look at that. Some of those are averaging 18 PV units. And then if you look at the time height section for variability of PV, it is a little bit similar. You have more variability here when the storm is strong. You have weak variability here, which I don't understand. And then pretty strong variability here. There's still quite a bit here too. Every storm is different. Looks like inertial instability might have played a role in the storm too. And here's the mean PV. A little bit similar structure. Why don't I have a slide that compares all these together, so let's do that. Okay, so Yasa, Harold, and Winston. Sigma PV and mean PV. Time height sections. Are there similarities or not? For sigma PV, these guys, some similarities. There's a diurnal cycle, but it's more obvious in some than others. This feature seems to be common in all three, as does this feature here in the mid-troposphere. More variability associated with vortex stretching and shrinking and stuff in the middle of the hurricane. As far as mean PV, also some similarities. Here's the vortex spin up the cyclonic phase in the middle of the troposphere. And then, yeah, there is this very potent inertial unstable region in the first one. And there's basic similarity. This is all, here's minus 0.1. Here's minus 0.1. So some features are similar. Again, this is kind of groping in the dark, trying to explore something a little bit new. So there, we thought we better look at maps at 50 and 70 hectopascals. This is Harold and Winston on the left, 6 hours apart. And you can see, doesn't this look like classical gravity wave patterns? So if you take a slice through gravity waves, it looks like V's, right? And then if you look down, it looks like where there's an updraft punching in the stratosphere right there. It'll look like a concentric rings, like throwing a stone into a pond. So I think these curved linear features are gravity wave-ish. So here's a gravity wave packet radiating up. It takes a while. So conclusions, part 2, finally. Studying the behavior of PV in high-resolution global data sets can lend insight into TC dynamics. The large values of variability in the UTLS and a pronounced diurnal cycle, together with weak inertial stability, occurred prior to and during the rapid growth phase of all three of these, although the signature in the diurnal cycle is weaker in Harold and Winston, or more irregular. And it may be useful for diagnosing and forecasting in storm growth and decay, maybe not at all, but it probably will at least help me understand hurricanes better because I need to learn more about them. The diurnal cycle, the nighttime deep convective growth, is well described by the sigma PV metric. So almost done. Come on in. And so I have a hypothesis for the second part is, if you do a simple calculation that if you have a 5 meter per second, 10 meter per second divergent outflow, then it'll go 300 kilometers in 8 hours, which is about the time scale indicated in Jason Dunyear's paper. So it may be that you don't have to invoke an extra heating by the sun on tops of tropical cyclones. Maybe you don't need that at all. It may be just an outward pulse required from a vigorous nighttime upward mass flux. It has to come out, and it takes a while. And lastly, UTLS PV dipole formation and IGW radiation are intimately linked with the adjustment process. And I think probably as a whole community of scientists that this may be an important thing to look into for a long time. All right, thanks for your attention.
We don't have time for questions, but if you have any questions, please run through the
Yeah, if you have a
comments.
class right at 1 o'clock, sorry about that.
Yeah, my class. But if people want to keep talking about tropical, they can stay here and listen to my class.
I should stay and learn more about TCs.
Thank you.